Well, hi everyone. This is an introduction to Chapter 17, which focuses on human health and environmental risks. The opening story highlights two issues. The first is how a grassroots effort worked to resolve a community problem, and the second reminds us of the prevalence of environmental problems associated with low-income minority populations. I've attached a short video to review this concept of environmental injustice.
Okay, so this is a city. Here are all the people living in it, people of all different colors, ages, wealths, and incomes. Except they don't all live together in the same place. They're separated into different parts of the city by what color they are, what language they speak, and how much money they have. And those different parts of the city look quite different. The parts that are whiter and wealthier tend to have green spaces, grocery stores with nutritious organic food, and of course the money to buy it, and are often far away from pollution-emitting freeways. The parts that are poorer and more diverse tend to have industrial sites, heavy-duty diesel-polluted ports and highways, and hazardous waste, all things that the city relies on to run properly, but that heavily pollute the air and water. And even if they had those grocery stores with nutritious organic food, most residents there couldn't afford it anyway. How did this happen? Well, this segregation can be traced back to race-based zoning and housing policies, but it wasn't always as deliberate as plain old racism. Some separations can simply be traced to poor land use planning. And as a result, these residents of the same city live very different lives. Say the city realizes it has an emissions problem. It comes up with a plan to reduce air pollution, plant more trees to suck up the carbon, or start a cap and trade program. But those trees get planted in the neighborhoods that are already green, and the factories that are spewing toxins into the air just buy more carbon offsets and keep spewing their toxins. The benefits of these programs are enjoyed by the communities that are already doing just fine, and the communities that were hurting most from all that air pollution, well, they're still hurting. This isn't just an imaginary city, this is the story of real cities all across the US where people might live in the very same area code, but their race, ethnicity, or wealth and income bracket causes them to experience wildly different quality of air, water, and life. In fact, it can even mean that they also experience different deaths. That's how serious this stuff is. This kind of inequity expands far beyond cities, too. Rural areas are full of commercially valuable resources like oil and coal, and they're also home to indigenous and low-income communities. But when those resources are extracted, those communities don't see any of the money, and they end up with all the air and water contamination that's left over from the extraction. And we even see this injustice on a global level, like in small island nations that are forced to directly confront the consequences of rising sea levels, but haven't played any significant role in the industries that are causing climate change. These peoples are sometimes forced to flee their homes because their land is literally going underwater. But the very states that did play a hand in creating climate change don't have migration policies to accommodate them. So when we talk about environmental justice, we're talking about how we can try to break down and reimagine a system that's built up on these inequities. A system where those who are already disadvantaged because of their race and economic status are made poorer because they're unable to profit from the resources that the world depends on, and are made sick or worse by the environmental contamination that comes with extracting those resources. Social inequities are intimately tied to the environment. That's why social justice is an environmental issue, too.
All right, well, I hope you liked that little video clip. The next slide is focusing on the three main categories of health and health human risks. The first is physical, second is biological, and the third is chemical. And I'll get into the biological and chemical in more detail in future slides. But in physical, it basically results in injury, and it could be things such as accidents or collapsing buildings due to earthquakes, something along that line. All right, if you're looking at these two pie charts, it looks at a couple things. One, if you're not already familiar with the terms chronic and acute disease, please reacquaint yourself with those terms. I'm focusing on the smaller of the two pie charts, and what this illustrates is the prevalence of 6 infectious diseases And we'll get into that shortly with biological risks. Biological risks are any type of infectious diseases that causes sickness, and those diseases are, those pathogens or infectious agents are called pathogens. Some very common pathogens: bacteria, viruses, parasitic worms. Examples of some of the diseases they cause. And then these would be diseases that are not caused by pathogens, which is represented by the other 50% in the larger of the two pie charts on the previous slide. The World Health Organization, or WHO, and that's a very good acronym to remember or at least be familiar with, basically looked at low-income and high-income countries and the prevalence of specific types of diseases. And what this allowed them to do was to provide pathways for combating these diseases. So in low-income countries, the goals are to improve nutrition, to clean water, and to improve sanitation. And in higher income countries, it basically has to focus on our lifestyle choices. Some historical diseases are listed below, and one thing to kind of get into your vocabulary terminology is the difference between an epidemic and a pandemic. Remember, just because something is breaking out in the state of Maine, it can be an epidemic for Maine, but it's not a pandemic. It needs to really spread over a large geographical area. All right, some of the historical diseases: the plague, malaria, and tuberculosis. Some historical diseases have been eliminated through immunization programs. Two examples that I could think of are polio and smallpox. And then there's many emergent diseases, and these are diseases that were at one time uncommon or rare, and now we're seeing much more prevalency of these. All right, the next unit of human risk is chemical risks, and they're categorized in, of course, a variety of subcategories like neurotoxins and carcinogens, teratogens, allergens, and endocrine disruptors. I'll provide you with some more specific details in the following slides. One other thing to recall in terms of vocabulary is that when we're looking at chemical risks, one field of study is called toxicology, and that is basically the study of chemical risks. All right, so carcinogens cause or promote the development of cancer, and I'm sure you've heard before cigarette smoking is carcinogenic, asbestos exposure, and so forth. Some of these carcinogens are caused by viruses such as the HPV, and there are vaccinations for some, not all. Neurotoxins impair the nervous system, and a couple of good examples of that would be lead, mercury, and PCBs. Mutagens basically cause inheritable diseases, so they modify your DNA. And teratogens are a class of drugs that cause birth defects. So they don't impact the adult, the mother, but they do impact the developing fetus. Again, mercury is a teratogen. So if you are exposed to mercury as when you're pregnant, it puts the fetus at risk for developing brain development failures. Also, consumption of alcohol can result in fetal alcohol syndrome, and the pictures to the right are examples of children who are born with that disease. There are some physical characteristics, but there's also developmental delays. And formaldehyde was a drug that was prescribed back in the 40s and perhaps 50s before it was banned, and that caused significant birth defects. Children were often born with no limbs at all. A dose-response study is the method that toxicologists use to determine safe values for human consumption. And these acronyms LD50 and ED50 should be acronyms that you can recall. So lethal dose that kills 50% of the individuals, or the effective dose that causes 50% of the animals to get to show some sign of sickness, not necessarily death. They use animal studies to determine these values, and they graph out some data, and you find where that 50% mark is, and that is your LD50. You might be given a table of data, and you'll have to graph it and come up with the LD50. So just be familiar with the looks of this and how you would set up your table. When they look at an LD50 value for animals, they then take that number and divide it by 1,000. And so in this way, the dose for humans is modified, and the lower the value of the lethal dose, that means the less you'd have to take in order for it to be lethal. Next slide is focusing on bioaccumulation as well as biomagnification. And I've got a pretty good video that not only talks about bioaccumulation and magnification, but really gives some good information about the EPA and its history. So even though you know a little bit about biomagnification, please stay tuned for this video because it's pretty thorough.
The 19th and 20th centuries were a time of huge advancements in industry and technology for the human race. The science of chemistry led to the discovery of new compounds and techniques for making chemicals. Those advances led to what are now literally millions of man-made products, ones we use every day, ranging from fuels to power automobiles and other equipment, to medicines, clothing, and household cleaning products, developed to meet ever-growing consumer demands. It's hard to imagine our world without the chemicals and products produced through modern chemistry. Unfortunately, up until the latter part of the 20th century, chemicals and chemical wastes were typically produced and disposed of without considering potential impacts to our land, air, or water, or our health. Prior to the establishment of the Environmental Protection Agency, there were very few laws and regulations to ensure the proper storage and disposal of chemicals and chemical byproducts. Very little, if anything, was then known about how these chemicals could affect people or the environment. Although these types of disposal practices were acceptable at the time, growing concern about waste and byproducts from the chemical industry, as well as worker safety, eventually led to increased government regulation. EPA was formed in 1970 for the purpose of regulating chemicals and protecting human health by safeguarding the natural environment, land, air, and water. Since its formation, EPA has worked to ensure proper storage and disposal of all chemicals. Strict laws and regulations have been enacted to protect our land, water, and air. EPA has also worked to methodically identify and clean up historical waste sites across the country, some of which are called Superfund sites. As part of their ongoing work to protect human health and the environment, EPA has identified a particular class of chemicals that deserve special attention and management. Collectively, this group of chemicals is classified as persistent, bioaccumulative, and toxic chemicals, or PBTs for short. These chemicals can remain in the environment a long time, and some may concentrate in the bodies of animals, including humans. PBTs include certain types of pesticides that were once used in the U.S., including chlordane, DDT, Aldrin, Dieldrin, Mirex, to name a few. PBTs also include mercury and mercury compounds, alkyl lead, which was the type of lead once used as an anti-knock compound in leaded gas, dioxins and furans, and polychlorinated biphenyls, or PCBs. PBTs are called persistent, meaning they are stable chemical compounds. Some do not readily break down easily. Due to their chemical structure, they can cycle between air, water, and land, and some can remain in the environment for decades. The result of organisms such as fish being exposed to these PBTs is called bioaccumulation. Bioaccumulation is the accumulation of substances such as pesticides or other organic chemicals through respiration, food intake, skin contact, and other means. They are bioaccumulative because they accumulate in living organisms, and the levels in these organisms can build up or concentrate over time with repeated exposures. They can be toxic, meaning they can cause health effects if people are exposed beyond safe levels. To understand how these chemicals may behave in the environment, let's look at polychlorinated biphenyls or PCBs as an example. PCBs are actually a class of over 200 different chemical compounds. They are comprised of carbon, hydrogen, and chlorine. PCBs were widely used in industrial and commercial applications such as lubricants and coolants, and in a variety of applications such as hydraulic oils, lighting and electrical devices, capacitors and transformers. PCBs were even used as additives in some paints. The production of PCBs was banned in 1977 because of growing evidence that they were persistent in the environment. Unfortunately, many PCBs had already been released into the environment prior to 1977 through disposal in landfills, accidents, spills, fires, etc. We now know that PCBs can travel long distances from where they were originally released and remain in the environment for a very long time. For this reason, PCBs are found virtually all over the world. People can be exposed to PCBs in the environment by breathing air containing PCBs, direct skin contact with PCBs or materials containing PCBs, or by ingesting PCBs in water and food. This is of particular concern because with repeated exposure, PCBs can be concentrated in the body over time. Let's see how this could happen. Once in the environment, most PCBs do not dissolve easily in water, but they will bind to the organic components in soils and sediments. This means they can be easily transported with particles washed into streams and rivers. When PCBs enter a body of water, they can become part of the food chain. This happens because the PCB particles bind tightly to organic materials like bottom sediments, which are eaten by small bottom-dwelling organisms. These smaller organisms are then eaten by larger animals, which can in turn be eaten by fish. Smaller fish can then be eaten by larger fish and other animals, including humans. Since these organisms cannot easily break down or excrete the PCBs, these chemicals can be passed along through each link in the food chain. This process is called bioaccumulation. Some PCBs can gradually become concentrated in the animal's tissues and can reach levels that may be many times higher than what was originally found in the water and sediments. Bioaccumulation of PCBs mainly occurs in specific organs and tissues. If the PCBs concentrate to a high enough level, animals can even become unsafe for people to eat. The extent of bioaccumulation varies depending on site-specific information, such as which chemical is present, how much of the chemical is in the environment, the organism being exposed, and how much the organism has actually ingested into its system. The bioaccumulation of PCBs and other PBTs is especially common in fish and seafood and can result in regulatory agencies releasing consumption advisories. People need to be aware of any fish or seafood consumption advisories for their area and follow published guidelines in order to avoid potential health effects. A consumption advisory is a warning. Its purpose is to make the public aware that contaminants are present in fish or seafood. Health effects could possibly occur if people do not follow the advisory guidelines. Advisories in the United States typically specify the following: type and location of contamination within a water body, the affected localities, the type or species of fish affected, and the number of locally caught fish or seafood meals the average person can safely eat each week or month from the advisory area. Certain fish bioaccumulate contaminants more than others. In addition, larger fish will typically have higher concentrations as well. Some consumption advisories provide more strict warnings for groups of people at higher risk, such as children or pregnant women. Or they might advise people to avoid eating any fish or seafood from certain areas. If you eat fish or seafood from areas of known contamination, there are steps you can take to reduce the amount of chemicals like PCBs that are absorbed into your body. Typical recommendations may include eating the smaller and younger animals who will have had less time to accumulate contaminants than the older, larger animals. Filleting the fish or removing skin, fat, and organs before cooking. Contaminants such as PCBs tend to collect and concentrate in fatty tissues and organs. Increasing cooking time and baking, broiling, or grilling on a rack to allow the fat to cook out. Battering and frying tends to trap contaminants inside. Discarding the fats and drippings that cook out of the fish instead of reusing them for stock or broths. Follow these simple recommendations and specific guidance published in local fish and seafood consumption advisories. Doing so will help protect your health and still allow you to keep locally caught fish and seafood in your diet. Thankfully, there are now laws and regulations to ensure the proper storage and disposal of PBTs. The EPA, the Department of Defense, and your federal, state, and local governments will continue to work in partnership to clean up past releases and minimize potential future exposures from chemicals like PCBs to both humans and wildlife. If you need additional information on fish or seafood consumption.
Okay, so that pretty much fills you in on everything you needed to know about safely handling fish in our waterways. But anyway, I thought that was a very good historical EPA summary sheet. The video did talk a little bit about the persistence of some of these chemicals, and just looking at this chart from your textbook, you can see that DDT can exist in the soil for up to 30 years. So these are, again, very persistent chemicals. And then to kind of end our presentation, we're going to talk a little bit about the Stockholm Convention, which is an international group of nations that gathered in 2001, and they were focusing on, again, these persistent organic pollutants, or POPs, and they created something called the Dirty Dozen at that time. And DDT, as well as PCBs, were on that initial Dirty Dozen list. This convention continues to meet, so it's not a one-shot deal. They meet, they follow up on substances that had been restricted to verify that, in fact, they were restricted. They look at new compounds, and they're constantly adding to that to that original Dirty Dozen list. And that concludes chapter 17. I hope you enjoyed this podcast.